Hi, today we're going to talk about least square minimization and linear regression. Linear regression is an old concept started from Gauss when he researched on the astronomical studies. And even in the 200 years, still a lot of people improve his method. For example, in the next few hours, we're going to learn the Kalman filter. And this advanced tool really based on the least square estimation. Let's start a simple question. We know the heavier the chicken, the more food it may consume. So let's assume there's a linear relationship between the weight of the chicken and the food it consumes. So you write into a straight line equation, and these two, beta 0 and the beta 1, we call it parameters. And in the geometry you learned, the beta 0 is the intercept on the y coordinate. The beta 1 is the slope. And we also know 2 points uniquely determine a straight line. If I give you 2 points here, one is when the chicken is 4.6 pounds, it consumes 87 pounds of the food in a month. Or another chicken, or the same chicken, 5.1 pounds, it consumes a little more. That's enough. You got 2 points on the straight line, and you can find the straight line equation by plugging in the x to here, y to here. You get this equation. And then the x again to here, the y to here, you get the second equation. Then, of course, you can solve it and find the equation. This is what we get as a straight line. Then the intercept is beta equal 31.9, and the slope is 12. Well, let's look at another question. You know, it's a little bit naive to make the conclusion about the relationship between the chicken and the food it concerns based only on 2 chickens. In reality, the manager may have to weigh a lot of chickens and also record how much food they consume in a month. And then we're going to get a table like this with 10 sets of data. And then we're going to, based on those data, to find the more reasonable relationship. So graphically, let's demonstrate. In the left hand, we have a graph. The 10 points are based on the data on the table. And we select the random 2 points. We draw the line here, and that's unique. However, on the right hand, intuitively you can think, even very clear, not a single line could pass all 10 points, but the green line on the right hand is crossed right in the middle. You might think, this one looks more fit to the data. So mathematically, how do you know which one is better? Well, the idea is called least square estimate. So we try to measure the deviation of all the points from the line like this. And then we try to measure which one have the least distance, roughly speaking. But a little more detail will tell you what is the least square. So let's generalize this idea. Doesn't matter if it's a chicken or is the product that you sell based on the investment in the advertising. You can have any application. What we look at now is the data set. Let's say we have n points, and they're scattered around the graph. We try to fit into a line equation. So the straight line needs two parameters, the interceptor and the slope. But if you put the x1 to here, when the I equal 1, you're going to get the y1 equals beta 0 plus beta 1 x1. And when you put the x2, you get another y2. But this y is a little different y. Let me back into the graph to show you what is the difference. See, here's the straight line. Let's say this one's x1. The y1 is right here instead of here. This is y2. The y2 on the straight line is here. Let me put another sign. Most of them are not the same as the y of the original data. That we call it the deviation, the difference between the data and your fitting line. Well, then let's look at the real y. The real y is here. It's not the same y on the straight line. That's when I take this hat off. Now I take that off. Then I got the real y. And you get an epsilon I here. This epsilon I, we call it the error from the data point to the straight line. So is the deviation between the y value in your prediction, that's your straight line, to the actual y value, that's your data. Now, keep that in mind, it's crucial. So, in another word, back to here, this is the epsilon 1, this is the epsilon 2, that's epsilon 3, epsilon 4, so on and so forth. And now, the idea is pretty straight. All we need is try to minimize this epsilon I square. That's why it's called the least square. Then you say, hey, why you want to square it? Well, the problem, if you just add this epsilon I, they're going to cancel out the errors. One overestimate, another one underestimate. In the end, you can cancel it out. You say, okay, you got 0 error. That's not true. You just cancel it out accidentally. The square, you know, positive or negative, you square is always positive. So error is error, all positive. That's why we put a square called the least square. Well, another alternative, you say, okay, how about let's add all this absolute value. That's fine, but the problem is the absolute value is not a smooth function. We're going to use the critical points to take a derivative, and that's hard from the square root. So that's why we use the square. Well, then you start from this equation. The epsilon I is simply yi minus this. So plug into the epsilon I to here, we get this equation. Each point you get a square. We have n point. We just add them all together. After you understand this idea of least square, the rest is trivial calculus. All we need to do next is take the derivative, set it equal 0, then we call the point as the critical points, and we have only one critical point. We take the derivative to beta 0, take the derivative to beta 1, and you get two equations. You only get two parameters, so no problem. We can solve this beta 0 and the beta 1 and by solving this pair of equations. Then we get the straight line. That straight line is called the linear regression line, or we call it, say, the linear fitting line. Fitting line. What means linear? Means straight line. Then we understand how we get this equation. In short, to get a straight line, you only need 2 points. But in our situation, you got 10 points. In real world, the problem, you can get hundreds, thousands of points. So you plug in the data, you get hundreds of equations, or 10 equations here. That's called the overdetermined problem. Overdetermined. The overdetermined problem is good if you focus on the error, and you know in real world everything has error. Try to minimize the error. This idea is called the least square error method. MSE. Okay, sometimes it's called the MSE, minimum square error. Okay, let's back to the equation to look at the example. In our example with 10 points in the data set, all we need is to follow the formula and to figure out the average of the chicken weight and the average of the food consumed, plug into the formula, and then we get this straight line. That's the green one on the right hand. Well, I will let you go home to do the homework. Then you focus on the detail of the formula. In here, let's focus on ideas.